Hey everyone, Mr. Newman here, and today we're going to learn about modeling exponential growth and decay when you're using the words percent increase and percent decrease. So, first thing, we do know the formula for the exponential function. That's f of x equals a times b to the x. And we've got names for those. There's a, which is the coefficient. That's the initial value or your starting value. And b, we call that the base. That is the growth or decay factor. The important word is factor because that base, that b, is the number you multiply by over and over in each iteration or each step. So the new words we're going to be using are percent increase and percent decrease. For percent increase, what we do is the growth factor, the number we're multiplying by, in other words b, is 1 plus the percent increase. So for example, if we have 6% increase, then b is going to be 1 plus that. Now remember that percent means out of 100. So in order to change percent to a decimal, which is what we're going to use to add, we need to divide that number by 100. So first of all, what is 6% in terms of a decimal? We'll divide about 6 by 100 and you get 0.06. So I'm going to add that to 1 plus that decimal, or 1 plus that number, gives me the percent, gives me the growth factor, which is b. So b is going to be 1.06. Notice 6% increase means 1.06 is what we're multiplying by over and over. If we have a 2.5% increase, divide that by 100 to get 0.025, and b is 1.025. For an 18% increase, that is 0.18. So when we add that to 1, we get 1.18. The reason that we add 1 is because whenever you're increasing something by a percentage, you always get that amount back again, and that is what the 1 represents. Now, for percent decrease, it's a little bit different. Instead of adding, we're going to subtract that percentage from 1. So it's 1 minus the percent. Notice these are all increase questions. The only thing I changed was change these to decrease. So 6% is still 0.06. 1 minus 0.06 is 0.94. So 0.94 is the growth factor or decay factor when we have a 6% decrease. 2.5% decrease is going down by 0.25. So subtract 1 minus 0.25 is 0.975. And the growth factor for an 18% decrease is 1 minus 0.18, which is 0.82. Now, one way to remember this is that whenever you multiply by a number larger than 1, it's always going to make it bigger. So if we're talking about an increase or growth, it's going to be 1 point something because we're increasing it, or a number bigger than 1. Whereas decreasing, decay, that is when you multiply by positive numbers smaller than 1. So we're always going to do 1 minus that percentage to find the decay percentage. The first three examples, 1, 2, and 3, were examples of exponential growth, while the last 3, 4, 5, and 6, were examples of exponential decay. So let's do some example problems. You deposit $200 into a bank account. Every year that account increases by 12%. $200 is our initial value because that's what we're starting with. Because we said it increases, that means it's going to be a growth. So we want to circle the growth right there. And the percentage is 12%, or that's 0.112. So when we say a growth percentage, that is 12%. However, the growth factor is what we multiply by each time. That is 1 plus that. So 1.12. And our equation is as follows. So remember the equation, the generic equation is a times b to the x. So we want to put the 200 in place of the a times 1.12 is the b. That's what we're multiplying over and over. And notice I wrote it a little differently. I put parentheses there. That's fine. That just shows that that is multiplication and the exponent is up there around the parentheses. Let's do the second one. The population of an apartment building is 4,000 people. Every month the population goes down by 12%. So that 4,000 is the initial value. That's what we're starting with. But because it says goes down, that's going to be an exponential decay. So the decay percentage is 12%, or 0.12. And the way we calculate the factor is take 1 and subtract that. 1 minus 0.12 is 0.88. So our equation is going to be 4,000 is the coefficient, that's the a, And b is 0.88, so it's 4,000 times 0.88 to the x. All right, I want you guys to try the next two, and if you get it correct, you won't have to watch it. You start a bank account with, okay, this is how you do it. You start a bank account with $500, so 500 is the initial value. And the tricky thing is interest on bank accounts, when you put money into the bank, it grows, it increases. So this is an exponential growth, which means we want to circle the growth for that 8%. 8% is 0.08, which means 1.08 is the growth factor. And f of x is 500 times 1.08 to the x. That's the equation. This one, go ahead and try number 4 on your own. All right, did you get it? If not, you're watching this. So initial value is $42. It goes down, so that's a decay. So 15%, 0.15, we subtract that, and we get 0.85 as the growth factor. F of x is 42 times 0.85 to the x. Oops. That's the equation. All right, now that we've found the equation, we're going to use the equation to calculate a value we want to know. So for this first one, for example, this is the first equation, or the first equation we found earlier. You deposit $200 in the bank account. What if I wanted to know how much money will be in the bank account in 3 years? That's what the question's asking. Well, we need to figure out, is this x or y? So it's helpful to have our variables. Notice that it says every year that account increases. That means that each or every, that years is what the x value of the input is. So I can label my variables, x is years, f of x or y is the amount of money in the account. That makes sense because if I plug in how many years I've worked or how many years it's been in there, I'm going to get out how much money is in the account. So we're going to plug in 3 for x because x equals 3. And so when I write my equation, it's 200 times 1.12 to the third power. And you can type all of that exactly as it is in the calculator. In fact, I would recommend typing all of it in, not in pieces. And when you do that, you get 345.6. Now we need to answer the question though, because 0.6, that doesn't look like money. And so we want to add a 0 there and put a $sign, put our units in front. And now it looks like money. So the $200 in 3 years became $345.60, which is pretty nice. For the second one, we again have the equation. We're going to do the same thing. I want you guys to try this one. All right, so here's how you do it. The population of an apartment building is 4,000 people. Every month the population goes down by 12%. So the population is the output, and the number of months is the input, is the x. Often if there's time, it will almost always be the input. So here we go. After 5 months, that's x equals 5. We're going to plug 5 into the equation. So 4,000 times 0.88 to the 5th. When you type that in, you get this number. However, people in the apartment building, this needs to be a rounded number. You can't have 0.9 people. So I'm going to round just to that. That 0.9 rounds up to a 1, so I get 2,111 people. Number 3. You can figure out the equation again, or you can look back at your notes and try to find it from up above on the same page. But the equation is going to be 500 times 1.08 to the x. How much money is in the account after 6 years? Well, the money in the account is the output, and every year, do you see that? That means years is the input, x. So 6 is x. So let's plug that 6 in for x. We get 500 times 1.08 to the 6th. And when you type in the calculator, you get this long decimal, but since it's money, we should round to 2 decimal places, and you get $793.44. Last one here. A certain stock is worth $42 at the beginning. That means it's the initial value. Every hour, that means hours is our x value now. It goes down by 15%. So this is exponential decay, like we said before. F of x is the stock value. X is the number of hours. That means x is 4. And when you type in the equation, plug in 4 like that, you get 21.92. Thank you very much for watching.